Okay, so this is basically, we're going to finish chapter 32. A lot of this discussion, we already did it in the lab, honestly. So we're going to finish this chapter by first of all revisiting the thing that we talked about in terms of the lab, and those are the phasor diagrams. I know, is Jackson in? Jackson is not here right now. That's the other person we're missing. Because last time when we did optics, basically, we did it. I remember when we were doing diffraction, we have a bunch of basically sine wave functions. Basically, a lot of signals that are coming from different places, and we use complex numbers to add them up. And at the end, we found the intensity of the beam when it combines different places, and we were able to get basically the intensity on the screen as it is coming and diffused through different angles. So we did that. We're using complex numbers because I asked you then, guys, do you want to do phasors method or do you want to do complex numbers? And I think Jackson is the one who stated there that we need to do it complex numbers, and you guys followed up with that. So we did complex numbers. And last time when I was also giving you the option, because we're facing the same thing. Every time we're combining basically waves or combining harmonics in general, you really can treat them whichever way. There are three methods, like I said. One of them is complex numbers, using also phasors method, or actually just hammering the cosine and the sine and adding them up one at a time. So you have choices really when it comes to that. But there is also actually the idea with the complex number or the phasors method is as long as you have a linear combination of some sort of this wave. If you have a linear problem, then you don't have a problem. You can use whichever method you like. And usually with the complex numbers, actually, the promise is the following. You have a very complicated problem, you cannot really work with it. I mean, you can, but it's tedious and long. And what you do in this case, you invent a new problem that is as tedious and as long as the first one. But when you combine them, somehow it becomes easier to work with. So that's the promise of complex numbers. Works beautifully too. With the adding and basically trig functions, it's usually very long, and sometimes you basically you have to be very careful with your signs and where the positive is, where the negative is, where the cos is, when the sin is. Once you find all of this, then you're also doing these things that way too. And also the phasors method, which can basically, as long as you're careful with your drawing and you know what you're doing, you should not have a problem. And that's similar to the trig function, to the complex numbers, basically. However, if you have problems that involve quadratics or anything that is non-linear combination of the harmonics, you cannot use complex numbers or phasors method. The only thing that is going to save you at that time are pure trig manipulations. And it's long, and it's even longer than the first one. And you have to be more cautious than the first two, actually, or anything at all. So that's basically the warning that I'm putting up front in here. And the good thing about this thing is most of the time what you do as an engineer is you make the problem linear. Once you're in linear mode, then you can choose whichever way you want to go and tackle the problem. So let me start with the RLC circuit again. That's basically the one that we're studying in this chapter. So we have a power source in here. And in here I have a resistor, and then an inductance, and then finally a capacitor. Usually we like to throw in a switch just to see what's going on at equal to 0. Now, the problem has an underlying feature that we don't talk very much about it, and the fact that there is a transient behavior first. When you turn on the switch immediately at equal to 0, the circuit starts to do other things on its own first, okay? And depending on the initial conditions, how much charges did you have in the capacitor to begin with? Did you have any currents in the circuit to begin with? If you have any of these two, or even if you don't have any of these two, the transient behavior first of all takes place. And the transient behavior is basically as if you don't have a at all. So if you don't have a power source, basically what you do in this case, the drop in voltage across the inductor, which is the second derivative of the charge with respect to time, plus the drop in voltage across the resistor, plus the drop in voltage across the capacitor, must then, in the absence of a power source, equal to 0. Solving this expression will usually give you something that I think you have seen in Physics 1, that is something that is in general depends on how L and R and C are related to one another. And you have three choices. Basically, you have a system that could be overly damped in the sense that the system, depending on the initial conditions, of course, will go like this, or it oscillates with damping. It goes to 0 like this, or critically damped, basically somewhere in between. And that depends on how L and R and C are related to one another. What kills the signal all the time, if you have an initial charge and a capacitor, and it's going to, there is no, there is no power supply right now. It's trying to push its charge to the resistor. The resistor will consume some of that power and dissipate it in the environment. Then they go through the inductor, then it goes through the capacitor, the resistor again. Every cycle, every second that the charge is moving through the resistor, the energy is dissipated, is lost. If the resistor was not there, then there will be a perfect oscillation between the capacitor and inductor, as we saw in the previous chapter. So there will be no loss in energy, and there will be no damping. So the reason why you have a signal that is going to, basically, you're going to lose charge at the end of the day is because of this resistor. The resistor will kill anything at the end of the day. So that's why your signal at the end of the day will die. Now, if on the other hand, you did not have a charge in here, but you have a current running through the system initially, and when you close the switch, that inductor now tries to push the current because it has an energy that is proportional to the square of the current, 1/2 of L times L squared. So it's going to push the current, build charges in the capacitor, run it through the resistor, and that is again where the drop in the energy is going to happen. That's where you're going to lose energy. So at the end of the day, this guy will run out of energy to push more current. When it runs out of energy, it's actually this guy that takes over because it will have charge. So they will try to build their oscillation on another, but every cycle, every time, the resistor is wasting energy one way or the other. So the transient signal dies out, basically, will cancel at the end of the day. So what remains at the end of the day, if you have a power source, is what we call a steady current or a steady state. The steady state now, so basically the entire signal now is composed of the steady state that is supplied by the power. As long as there is power, there will be always, no matter how much the resistor is dissipating energy, there is always a power source. The plug is always there in the wall, and you're always pulling energy from it. So that's what we call the steady state. So we have the steady state. This is supplied by the power source, and you have the transient. The transient, if you wait long enough, is going to die out. So that's basically what the thing is. The transient depends on the initial conditions, Q0 and I0. So if that depends on them. Now, even if you didn't have them, even if there was no Q0 and I0, the fact that the steady state wants to build voltage, it's going to trigger them. It's going to trigger the transient. The only thing about the transient is it's going to go away. The thing with the transient is, if you are within its time when it exists, it could overwhelm the steady state. It could spike up so high. That's why you use surge protectors. I mean, I don't know if you notice the sparks when you pull the plug from the wall, or you try to plug something and you see sparks flying. That is because sometimes that's really the transient behavior. And then after that, everything is smooth. That's why you have to protect your devices, your electronics, everything behind the scene. Otherwise, the transient can be disastrous. So here is what we're saying. We are going to wait a long time so that we don't deal with that nasty thing. So we're not going to be dealing with this one, and instead we're going to focus on the steady state. So that's basically, so we waited long enough. Remember, the transient is related to tau L, the time characteristic for the inductor, and tau C, the time characteristic for the inductor. And actually, that's basically how it depends on these two terms. Somehow there is a combination between them in there that is going to involve the L and C. But if you wait long enough, which is really not long, I mean, a few seconds, depending, because these things are measured in milliseconds or it's a very small unit. If you wait a second, 2 seconds, the transients are gone and you're dealing really with a steady state. If you take DPQ in math, if you're required to take it or you opt to take it, they have different names for them. The transient, they call it the homogeneous solution, namely the solution of the differential equation with no power source, with no external excitation. And the steady state, they have a different name for it. They call it the special solution. So there is a theorem in calculus later on. You can prove and show that the general solution to a differential equation of this type has two solutions. Has a special has a solution that depends on two constants, namely those are the initial conditions. That is called the homogeneous solution. So you solve this equation with 0 on the other side, and then you introduce the external term, which is the excitation, and you hunt for a special solution. Any special solution will do. And that is what we call a steady state. So that's basically what you do in DPQ, and you spend a good semester trying to work out this kind of differential equations and other things and different situations. As a matter of fact, if you take DPQ, most likely you're going to see this equation again. They give you this RLC circuit and they start working with you on it. If you're not going to take it, forget it, just focus on these two ideas. The fact that we're studying the steady state does not mean it's the whole picture. The whole picture includes the transient. So if you're trying to meet some sort of initial conditions or trying to have problems and you're trying to deal with it, you have to pay attention to the fact that this is not a complete picture, what we're about to do right now. Like the problem with the lab, for example, that was actually the steady state all along. It depends on V naught. Let me go back to the lab because that's actually our starting point. Let me go back to the lab and see what we are on the lab. Jonathan, did you attend the lab? The lab?
No, I didn't.
Okay, very good. Because you missed a lot. Okay. Sorry, I didn't mean to be very good, but just to make sure that my information is correct in you.
Yeah.
Okay. Okay, so let me go back to the lab. And let me explain what I'm talking about in here. Remember, this is the RLC circuit that we have. It's the same thing, basically. It's Ohm's law. Okay. I mean, Kirchhoff's rules, I'm sorry. So what we're saying in here, this is the signal. The fact that the solution to this equation is really not a complete statement. This is not the full solution. This is the special solution. Why do I say it's a special solution? Because if I put V naught equal to 0, this solution goes away because Q sub t becomes 0 and I sub t becomes 0, D sub t becomes 0, dr of t becomes 0. All of them, they're dependent on that V naught. So if you kill the power source in here, there is no solution. So this differential equation definitely has a solution, and that is what I'm talking about in terms of transient. So this statement in here is not really 100% complete. It is complete only in the sense that we have waited long enough, times that are longer than tau L and tau C. Okay, times that are of the order of a second or at least fraction of a second that is bigger than a millisecond. So if you're in that time frame, then this is okay, but you can say approximately this is the solution. That depends on V naught. But there is another part to it that we're not talking about, and it's really not a focus right now. So the focus is going to be on this permanent behavior. So again, we looked at that, and let me go back into this. My screen. Okay, I did not really go through the entire homework problems. So you may have one of the homework problems that deal with that part. So you are forewarned, okay? So you know what's going on. Now, having said that, I may have to change the instructions of the lab a little bit and something of the homework so that you're aware of this thing, okay? So I reserve the right to go back to the transient, okay? Something that, oh, you said you didn't do it in Physics 1 when you did the forced harmonic oscillator. But that's fine, we're doing it now. So this is exactly the forced harmonic oscillator, except that this is, if you wish, the forced RLC circuit, okay? And it is forced because you have that power supply. You have this V naught cosine of omega t. So basically, you send a signal, which is V naught cosine of omega t, and the outcome is something to happens to the charge, which turn out, and we verified it already in the lab, that it is something that is of the order of, first of all, you have omega and z, and you have V naught, and it's a cosine shifted by an amount phi behind it. Okay? If we take the derivative of this expression with respect to time, what is my expression here? I'm sorry, sine. Did I say cosine? It's a sine. The solution is actually a sine, not a cosine. Okay, it's the current that actually has a cosine. All you have to do is take the derivative of this expression with respect to time to find the current, I sub t, which is just the dq over dt of this expression, and that cancels the omega, and you'll be left with V naught over z times the cosine of omega t minus phi. Okay? Now, the inductor, let's start with the inductor first, because one thing, first of all, the V across the R is just R times the current. This is Ohm's law at its best. So it's R times this value, so it's V naught R over Z times the same cosine. And that was one of the points in the lab that says that, hey, we're supposed to have the current, but we don't have the current since we have the V sub R, and we're looking just for the phase. The phase then of V sub R is exactly the phase of I sub t, because there is no phase shift. You just multiply the current by number, by R, which was 5 ohms in the lab. So whatever is the current multiplied by 5, and you're good. So that's basically what that was talking about. So in other words, the voltage across the resistor and the current are in phase. Where this one is, if this is the whole thing is 25 degrees, so is this one is 25 degrees. If this reaches 45 degrees angle, this whole thing reaches the same angle in the same time. So they're in phase, they're in sync basically together. Now, if we were to find the B across the L, so that is going to be what? L times the derivative of the current with respect to time. This will pull a minus because of this expression. We'll pull a minus because of the cosine, and we'll pull another omega, and we multiply by L. L times omega is XL. XL times V naught with a negative sign, XL over Z times the cosine of omega t minus phi. There is an identity in trig that basically says cosine of any angle alpha, add to it pi over 2, is negative cosine of alpha. I'm sorry, did I say cosine of alpha? It's a negative sine of alpha. I'm sorry, sine, not cosine. I'm trying to get my, okay. So sine of that angle, let's see why is that. Sine cos, that's 0. Cos sine, no, actually this is a positive, I'm sorry. Okay. And we need the other one too. We need both of them too, actually. Sine of alpha minus pi over 2, this one is going to be equal to a cosine with a negative cosine of alpha. Those are the two identities we need for our stuff in here. Okay. Are you guys familiar with this trig identities? Sine of alpha minus pi over 2. This is simply sine of a plus b, which is sine cosine plus cosine sine, except they have a negative sign in here. So you can check yourself that this is correct. I have a minus times the cosine. So this is what I'm facing with as far as the voltage. So it's, wait a minute. Did I do it correctly in here? Minus cosine alpha in cos. Yeah, I think the identities are correct.
Isn't it
Sine
supposed to be
cos.
sine? Real?
No, this is correct. I think sine cos, that's 0.
No, I mean
Minus,
above the v sub l.
yeah, there is a we're taking the derivative of the current. Oh, you're right. You're right. You're right. That's where the trouble was. Thank you. So when you take the derivative of the cosine, it's actually a negative sign. So that's where the trouble is. But the identities are correct. So this is actually correct. This is a sine. So when you take the derivative of the cosine, it's a minus sign. So actually what we need in here are the sine, not the cosine. So let me flip this. We don't need this relationship. If I can find those tools again. We don't need this. We don't need this. We need another identity actually. We don't need this. And we don't need this. And let's remove the signs in here. Thank you. So what we need actually are the cosines, you're right. So cos of alpha plus over pi over 2, that is what we are looking for. And cos of alpha minus pi over 2, cos, that's 0, minus sin, so this is a minus sine of alpha. And this will be a positive sine of alpha because cos, that's 0 because of cos of 90 degrees, plus sine of sine and sine, so that's sine of alpha. So that's correct. So this will be then cosine of the entire thing added to it pi over 2. We change the sign. So the voltage across the L, V sub L, then is going to be a positive first of all. And whatever coefficients we're going to leave it as. So it's V naught XL, V naught XL over Z times again cos of omega t minus phi added to it pi over 2. That ensures the negative sign in the front. Negative sine times sin. So this is correct. If we do the same thing for the voltage across the capacitor, the voltage across capacitor, by the way, it's the Q itself, whatever the Q was, it's this whole thing, basically divided by C. So I will have 1 over omega times C, which is XC, and so the whole thing will have a sign in it. So VC now will have B naught 1 over omega C, that's actually XC, divided by Z times the sine of omega t minus phi. And this is the second one. It's cos of this whole thing minus pi over 2. So VC, I can write it again as V naught times XC over Z times the cos now of omega t minus phi minus pi over 2. We wanted everything in cos because of the following reason, and I will tell you why. DC now is something times the cos of some big phase in here. Omega t minus pi over 2. DL is also something in here times cos of something, which is omega t minus pi over 2. DR also is something in here times cosine of something, which is omega t minus 5. So two of them have either a positive pi over 2 or a negative pi over 2, and one of them does not. But all of them are cosine. So what a phasor is, if I give you a wave, and I tell you this wave, or I'm sorry, signal, this signal is changing with time at a rate of omega t. So here is that signal. Here is omega t, and this is the length of that basically signal. This is the intensity of the signal. So let's call it S. What I'm looking for is its x component. The x component now here is clearly S times cosine of omega t. S times cosine of omega t. Now, if this is spinning at the rate of omega t, then it's going to spin. Sometimes it's going to be maximum when omega t is equal to 0, or 360 degrees, or whichever your choice. It's going to be negative, whatever S, when it's 180 degrees or 360 degrees plus that. It's going to have zero projection when it's 90 degrees or below 90 degrees, and anywhere in between them. So the phasor actually describes, if I draw a vector in here, whose length is S, and whose direction is the phase itself, then basically this is a representation of all of my signals, provided everything is in a cos. Okay? If I'm doing things in sine, then I have to convert everything in sine and start flipping my x-axis and y-axis. The convention is stick with the cosine, because that way everything is on the x-axis, you don't have a problem. So that's why the intent was from the get-go, since everything is the same, is to start with a signal that is a cos itself. So do not do something else, okay? If you do it, just wait 90 degrees so that it becomes a cos, because the sine and the cos, they flip one another, they become one another just after pi over 2, I'm sorry. And that's actually because of this identity too that we used in here. That's what the cos and the sin, they are identical because of this one. That's what we used actually to get to this expression. So if, in other words, if the signal was given to you as a sin, just leave it as is. Just say that it's a sin with a 90-degree phase shift, and everybody else will be shifted by that amount. So the idea is this identity is the one that drives everything. Those two identities. As a matter of fact, the first one is, because the plus in here, if you want to change it to a minus, the second expression you recover. So this sign and that sign, they're opposite to one another. That's all. If this is positive, this is negative. If this is negative, that's positive. So having said that, let's see now how the picture looks like for my RLC circuit. What's going on? First of all, the voltage itself. So this is the okay, so this is my x-axis and y-axis. So I'm going to start writing the signal itself has this value, which is V naught, the length, and it's making an angle of omega t. Okay? And I'm going to refer back to omega t as 0 as a matter of fact. So because omega t is the same shift, omega t, and omega t in here, and omega t in here. So since omega t in every one of them, I'm going to take omega t to be 0. As a matter of fact, that is my starting point in here. Or I'm sorry, that is my starting point for the entire signal. So this is my starting point now where the signal is. Yes, it's omega t, but I'm going to be, how should I put it? Measuring things from this point on. So if I do that, then my current is at an omega t minus phi, whatever that phi is. It could be any number, but it's a fixed number. So I'm going to have a different color in here to draw with. So let's assume that phi is so much that my this happens to be phi. Okay, and if that's phi, this angle now is omega t minus phi. And this length in here, I chose it on purpose to be exactly equal to R, times V naught over Z. So if this was V naught, this would be R over Z. I know you're probably saying that, hey, Z probably is bigger than R. You're right. But let's leave it for right now, at least the picture, so that we can see it. If not, make this one a lot bigger. Okay. So the length of this one is V naught times R over Z. So that's the voltage across the R capacitor. Now, if I add 90-degree angle to this guy, that should put it in here. Okay. This has length of V naught times XL over Z. And this is a 90-degree angle from where the current is, or the voltage across the resistor is. So this is a 90-degree angle. That's exactly what I mean by this expression here. Where is it? Omega t minus phi plus pi over 2. And this is the strength of that vector. Now, in the same token, the other one, XC, is lagging behind. So let's draw this one as being V naught times XC over Z. That is the length of that vector. Okay. So what we did in exercise 1 from the lab, actually, add this signal to this signal to this signal, and we found to be equal to this one. I know I draw it a little bit smaller. I should not. Probably it's a little bigger than that for V naught. But the point is just to see it pictorially. That's all. With this phasor thing. Do you guys understand? So basically what I'm saying in here is take this quantity. Let me draw it with a different color so that we see you. Grab this color. So take this quantity and subtract them from one another. You probably will find this much. Okay? And then add them to this number. And this is the sum. This is actually V naught. Okay? This is what the V naught is. So that's the exercise number 1 from the lab, is add up the signal from the resistor, time and everything, because this expression is changing with time. This whole thing, as t changes, this picture rotates and spins in space. Okay? You guys understand the idea behind it for the phasors? As a matter of fact, we can try to draw the whole thing at when omega t is equal to 0. Or when omega t is some angle, let's say 45 degrees. We start from 45 degrees and start drawing. So the point being in here, as long as you have a starting point for your signal, then you're going to go phi back. Now, phi might turn out to be a positive number, okay? Because it's still XL minus XC. This length can be bigger. So in other scenarios, you might have XC bigger. So in a different picture, probably you might have this one here, extending here. So XL minus XC might be a negative number, and the whole thing probably adds up to this signal. So this will be your addition in here. So in this case, this is in a capacitive circuit, whereas in the first one, it's an inductive circuit. You guys understand the idea behind it? I know we did the discussion earlier. Are you guys looking at the same screen, or am I not sharing the same screen? Because John has a question. Both aren't working in my calculator. What do you mean, John?
That was from a lot earlier, I think, when you were going over the equations.
Yeah, I got it figured out. It was
okay.
Yeah, it was just the identities you were doing.
Okay, very good. Thank you. Okay, the point being in here, as long as we're following this discussion, I guess we're in good shape in here. Basically, that this whole thing in here in terms of the phase, that it's really a vector representation. You don't need, once you have mastery over the those vectors, the rule is the following. It's always a 90-degree angle with respect to the current. So it's a good idea to start actually with the current. Forget about the voltage itself, okay? So the current is actually VR, so that's we're clear on that. So we're going to draw this thing in here with VR in starting point. equal I don't know what. Okay, so this is the current which is actually VR. I'm going to go 90 degrees above, that is going to be VL. I'm going to go 90 degrees below, and I'm going to be VC. That is it. This is VR, this is VC, this is VL. How it spins, that's up to it. Now, if I add up these two numbers in the y-axis, if you want to call them the y-axis, and their sum is here, so this is actually where the voltage is. This is the actual V, the power source, and this is the phi, the phase in this case. If I add them up and the sum is somehow here, XL minus XC, then the sum is actually here. This is what I mean by VL. I mean, so the power source, V0, basically the actual source that created these two things. Okay? They must add up according to the lab 1. So basically that's it. As long as you can start from the current, if you can give the current some sort of a shape, then add 90 degrees to it. Don't forget that VR is simply R times whatever current. VL is XL times whatever current. And VC is XL times whatever current. So do you guys have an understanding of what these phasors are, at least the idea behind them, especially in light of what we did in the lab? Yes? I suggest that you read through these things. Honestly, myself, I don't care which method you do. As long as you have an understanding of these things and how they work. If you're trying to solve a problem, you should be able to face it this way. Now, I think almost all of the homework problems except of 2 are of an RLC circuit in series. They all fall under the same category. That in this case, the reactance, which has the same units as the resistance basically, for the inductor is equal to omega times L. It's clearly that this quantity is very small for low frequencies and very high for higher frequencies. The reactance near the capacitor or on the capacitor is 1 over omega C. So this is what we call the reactance. Okay, and then it's also very, very high for low frequency and very small for high frequency. So this is the opposite because omega is downstairs now. The reactance for the resistor is actually R itself, if you want to call it XR. All of them, they are measured in the same unit. So the reactance is measured in ohms. All of them. As long as L is in Henry and omega is in radians per second and C is in farads and R is in ohm, everybody comes out to be in ohms. That's why the comparisons are perfect in here. Now, the omega itself, the Z itself, which is also in ohms, by the way, Z is the entire impedance for the circuit turned out to be, and we have seen that, XL squared minus, sorry, did I do XL squared? It's XL minus XC, the whole thing squared but under the square root. Okay? So that's basically what the impedance is, and the impedance is similar, if you wish, to that, to resistance. Now let's talk a little bit more about that circuit in here. This is how I'm going to draw my circuit right now. I'm gonna have the power source, which is just a V0. I'm gonna have my resistor drawn as just a normal resistor. I'm gonna have my inductor. I'm gonna have the capacitor at the end, and I have my switch in here. So if we do that, if we write the circuit as such, basically, let's throw in a switch in here. If we do it this way, so this is my XR, this is my X, this is my my L, and this would be my C, of course. And knowing what we know now in terms of what these expressions are, then we can write Ohm's law, basically for each and every one of them, saying that basically the voltage now for the entire circuit with the phase shift, and that's what you have to be very careful in here. That phase shift plays a major role. So it's not simply adding up those quantities and saying it's equal to that times the other one. Actually, is equal to Z times I, where Z is given by that expression. So it looks like it's not just adding, because drop across each and every one of them. This will be simply XR times I. This will be simply XL times, times also I. And this is times I. So the voltage drop across each and every one of them, the intensity of it, the value of it, the numerical value of it is that one. So this I is the I max. So if you're trying to find the voltage max, this is what you do, I max times XR. If you want to find the voltage maximum across, that's what you do. But you don't just add up those numbers to find the entire voltage. You actually use the triangle identity in here, okay? Because they are not all in the same direction to add them up. It's like vectors. Since vectors now they're in space, you can't just add them up. It's not like, for example, you have a resistor 1, resistor 2, and resistor 3, they're in series. Then you add them up and you have the overall resistor and you're in good shape. No, you don't do that, because now, because of this, you have to be very careful in here. So the voltage is given by that expression. So this is the maximum voltage, this is the maximum current, and this is the impedance of the circuit. Okay? So I hope this idea in here, and we use some sort of a similarity with the DC circuit. We're not doing DC anymore, but we're using a similarity with it using this approach. So that's basically the idea behind the whole thing in here. Well, unless you guys don't have any questions, because there is another point that we need to get to, and that's namely the power. Oh, I'm sorry, there was another point also that I was trying to get to. For the lab, for the homework, there are two problems, I think 54 and 55, or 50, yeah, 54 and 55. They have a different configuration. They have a power source, but these three things, they are not in series, they are actually in parallel. So you have a picture for the homework problem. So the discussion, you have to be very careful in that. So basically, you have the power source, and you have R, you have L, and you have a capacitor. So in this case, the circuit is completely different. So V is the same now, but the current splits itself now into I in the resistor, and I in the inductor, and I in the capacitor. And this sums of the three I's are actually equal to I. So the whole discussion for those two homework problems, they're similar, except instead of doing Kirchhoff's rule for the voltage, you're going to do Kirchhoff's rule for the current, and the whole discussion will be similar, except that the expressions now are a little bit more different, in a sense that you have to satisfy that voltage drop in there. Okay, so that's for another thing in there. But as a matter of fact, using this very similar analogy, you can actually do the discussion here and find that the 1 over Z in this case will simply add up in a similar fashion. 1 over Z will turn out for the homework problems. I'm discussing a little bit of a homework problem. Is going to be 1 over R, and it's this R, plus 1 over, what is it, X minus, or 1 over, anyway, we can go through the problem in there in more detail and find it, okay? But the analogy, you have to be very careful for it for this circuit in here. It's not similar, okay? It's not 100% exactly the same thing like this, the first one in there. Because there is a phase shift. There is no phase shift between this current and the voltage across in here, but there is definitely the current in here is not in phase with the voltage, and the same thing with the current in here is not in phase with this voltage in there. And there is a 90-degree shift for both of them in that. Anyway, let's go back and to finish this discussion here in terms of the power. So the voltage coming from the power supply, which is actually given by the EMF, is equal to V naught times some cosine of omega t. That is the voltage across the power source. We're going back to the series circuit now. And the voltage and the current turned out to be, if I remember the expression for it, had a cosine also. Yeah, it has a cosine. it was a V naught divided by Z times the cosine of omega t minus 5. So again, those are the exact same things. I told you guys to correct it because there is a mistake on that expression. It says V naught over omega. I hope you guys paid attention to that and you have it correct. So V naught over Z. So this is basically the how much its power, how much basically the voltage and the current across the actual power source itself. Now, if I want to find the power from basically from before is just the current times the voltage across the battery. So basically the power source, this is how much power it's delivering, how much energy it's giving every second. Then in this case, all I have to do is just do the product of these two. And this is time dependent because again, this whole signal depends on time. So the power is going to be V naught squared, because you have a V naught and a V naught, divided by Z times the cosine of omega t times the cosine of omega t minus 5. So in other words, this power depends on time. Let me write this expression, let's see, minus 5, sorry. So this is how this power that is drained from the source look like. We can use an expression in here for the cosine of omega t. I think it's cosine omega t is cos plus sin. So this expression for the power then look like this. P sub t then equal to V naught squared over Z times the cosine of omega t times open parentheses cos of omega t cos of phi plus sine of omega t sine of phi. Don't forget I have a cos multiplying them, so I will have a cos squared of omega t times cos phi and cos times sin, which is of omega t times sin phi. So basically the power look like this. P sub t will have V naught squared over Z. This you cannot do with the phasors or anything else. You have to do it with trig. So cosine of squared of omega t cos phi plus cos times sine. And cos times sine, I know cos times sine is just 1/2 of sine twice the angle t times sine of phi. Furthermore, there is another identity in trig that says that cos squared minus sine squared is equal to 1. So if you move multiply divided by basically what sine squared. I'm sorry. What is it? You divided by cos squared, yes. So you'll end up with something that looks like this, basically 2 cos squared. That's I think what the identity says. Minus 1 is equal to, what is it? Equal to no, it's not minus 1. That's in hyperbolic functions, actually. I'm sorry. Cos squared, it's a cosine of twice the angle, okay? So this whole thing is a cosine of twice the angle. I'm getting my trig functions and hyperbolic functions confused a little bit. Okay, so at the end in here, what we will find is cosine squared of omega t is simply equal to 1 plus cosine of 2 omega t divided by 2. So we're going to use this expression in here to get rid of that cos squared. And I have 1/2 in here, and I have another 1/2 in here, which I'm going to pull from both terms. And that gives me the power to being, as a function of time, V naught squared over 2Z times 1 plus of the 1/2, which is the 1/2 is out. So I have cosine of, I'm sorry, 1 times cosine first. Don't forget I have the whole thing is multiplying by cosine phi. So I'll be left with a cosine phi in here. Cos phi. And then I have a cos phi multiplying that cos of twice the angle. So in other words, I'll have plus cos phi cos of 2 omega t, and then I have another part in here that is left, sine 2 omega t times sine phi, because we took the 2 out as a common factor, plus sine of 2 omega t sine of phi. The last two terms, they add up to cosine of the sum of the two, or difference of the two angles, basically. So that's also another trig identity. So at the end, the power looks like this. P sub t is z squared over 2z times cosine of phi, that is by itself, plus cosine of 2 omega t minus phi. Minus phi, I'm sorry. I needed some more real estate in here. So when we average this quantity, the cosine of 2 omega t minus phi is oscillating. It's going up and down, up and down, up and down. So sometimes it's positive, sometimes it's positive and negative. So its average is going to be 0. That's basically what we will find. So, but the average of cosine phi is not 0. So because the power, I mean, the entire signal changes at the rate of omega, and then it's the frequency is what, 60 hertz. So every second, there is a 60 cycles up and down. So the signal at the end, what matters is just the average of it. So P on average is going to be V squared over 2Z times cosine of phi. That's it. The time-dependent part is gone. I think one of the homework problems asks you to prove that or show that or something like that. But remember, when we did also the previous, or at least the previous lesson, that v squared over r over v squared or v naught and v naught over square root of 2 is actually v RMS. Anything over square root of 2, I naught over square root of 2 is actually also I RMS. So this expression looks like then P bar is equal to V RMS squared over Z times cosine of phi. And cosine of phi from the lab, I think we showed to be R over, when we did that, we did the cosine of phi, we needed it in the calculation. When we were adding those two signals, it turns out to be R over Z actually. It's R over Z. It refers to the lab from today actually. That's what the cosine phi too. Remember, tangent of phi is XL minus XC over R, and we worked the algebra and everything else, and we found that actually R over Z turned out to be exactly cosine of phi. So basically, the power supply then looks like P bar is equal to V RMS times V RMS over Z times R over Z. Well, this expression in here is actually I RMS, because the I itself, the maximum current, is just the maximum voltage over Z. So if they divide both expressions by square root of 2, this expression still holds true. Namely, V maximum is equal to Z times I. That's what I wrote earlier, maximum. But if I divide both of them by square root of 2, this becomes VRMS, and this becomes IRMS. The root mean square. And at the end, basically the expression VRMS over Z is no more than just IRMS. So the entire basically expression can be expressed as follows. The power on average is given by I RMS times V RMS times R over Z. Okay, or cosine of phi. That's R over Z is cosine of phi. So that's basically in a nutshell how the expression looks like. You can write it in many, many ways now. You can write it in terms of V RMS if you like. times squared times R divided by Z squared. However you write it, it's going to be the same thing. So we can write it also as V RMS squared over now Z squared, because I have a Z already and I have a Z in here, times R. Times R. So it's Z squared and an R in here. So all of these expressions are equivalent to one another, and basically they boil down to the same thing. Now note, Z squared now is equal to R squared plus that expression. Z squared is not just simple expression. Z squared depends on actually on omega. It's equal to, I'm going to write it with omega itself actually. So this is how Z squared look like. So this expression depends on omega big time. If I have high frequency or low frequency, the signal changes differently. So this is how I'm going to write it finally, the expression in terms of omega. P on average depends on omega. The average power depends on omega. First of all, VRMS squared and times R divided by R squared plus omega L minus 1 over omega C, the whole thing squared. I'm going to multiply by 1 R and divide by R. The reason why I do that, I want this number to be a dimensionless number, because I have R squared, ohm squared, and I have ohm squared. So all the units of the power are carried by this expression in here, which has 1 over R in it. So basically, the power then depends on, I'm going to call the following expression here, P naught. That's going to be VRMS squared over R. This is in watts. This expression, the bigger they are, the smaller it is. The smaller they are, the higher it is. So it's this coefficient in here. Okay? And this expression here doesn't depend on anything, because it's, I mean, it depends on omega and L and R and C, but it has no units, because the numerator is in ohms, and the denominator is in ohms. I mean, ohm squared, and they cancel. So at the end of the day, this is a number like 12 or 13, whatever it is. It's just a dimensionless number. So the entire power is expressed in terms of that power. And the VRMS is the VRMS. In the United States, it's 120 watts. Okay? Most of the time it's fixed. So the higher they are, the more the power, the higher they are, I'm sorry, what is it? The smaller they are in here, that is, the higher this P naught in. It's more peaked, if you wish. Okay? Let me draw this function in here for you guys quickly to see how this looks like. So this is the power as a function of omega. The power is always positive, of course, because it's something that is positive. Omega is always positive, so this graph looks like this. For extreme high frequencies, when omega goes to infinity, this dominates, omega L dominates, this becomes 0. Omega L dominates, becomes omega L squared dominates, and R squared is neglected. So at the end of the day, you will have something that is going to blow up. You will have R over omega L, so it's going to go to infinity in the denominator, which means that this expression will be 0. Here. For omega very small, this will be negligible. 1 over a small omega in here will be big. When you square it, I know it has a negative sign, but when you square it, it's going to be positive. It's going to dominate this expression. So this will be eliminated. So at the end, you will have 1 over omega, which is big, but omega will go upstairs. So the whole quantity becomes small again, because they're dividing by something big. So it's going to be small. Somewhere in between them, the signal peaks. And it peaks at when this quantity is 0, when this number is 0. And that number is exactly 0 when omega L minus, so there is a frequency in here, which we're going to call omega C, omega naught, I'm sorry. That omega naught is critical in when omega is equal to omega naught, we have this expression vanishes. This is equal to 0. That means if I solve this equation for omega, I will have omega squared is equal to 1 over LC, namely omega is equal to 1 over square root of LC. Omega is positive. Frequency is always positive, so don't be tempted to put a negative sign in next to the square root. So this is the value where that makes the power at its max in here, okay? And that too will make the current max. That will make everything max. That's, remember, that I think the last part where everything maxes around that value. So the resonance frequency, this is the resonance, what we call resonance in here, where everything maxes, where all of everything starts to become maximum. So this is your omega naught. So this is the natural frequency of the circuit. So if you're changing your omega, remember the signal has a V naught and cosine omega t. But if you start playing with omega, start to change the dial on omega, you will peak at omega naught, and then anywhere outside is not peaked. Let me see if I have my GeoGebra function in here plotted for you guys. Let me stop sharing this thing in here and go back into my GeoGebra. The math here is exactly what I was talking to you about. I have an A term in here that represents the ratio of L over R actually. And I have a B parameter that represents the product of R times C actually. And this whole function, the one that dimensionless function, basically after you divide by R, is what really dominates. So the one in here is actually the maximum power. So that P naught that I wrote earlier is the peak of the power. It waxes at P naught. And P naught in here for small r is very sharp. It goes very high, okay? And for big R, it's going to be actually lower. But it broadens also, actually. That's one of the homework problems. You're supposed to find the gap at exactly halfway. Halfway is somewhere in here. This is 0.5, somewhere in here, okay? Half of this 1 is 0.5, and 0.5 is somewhere in here. And you're supposed to find it in the lab and see how that depends on R. The bigger they are, the broader it is, but then the whole signal peak slows down. So if you want to have sharp reception, make the R as small as possible. In other words, if you want to have your tuning device in here, let me change C now, the capacitance in here. First of all, look at the signal shifts now, okay? As I play with this one. If I change A now, the thing also starts to broaden in here, okay? But at all times, the intensity stays at 1, okay? This is one of the powers, by the way, I didn't tell you about GeoGebra. Hopefully you guys have time with it, and I know Jackson mentioned that your math teacher is using it. That's very good. You can do derivatives using it, actually, because I wanted to see where this thing vanishes to find the maximum and the signal. It's not exactly actually at omega naught, but slightly next to it when this thing starts to become 0. So this is a derivative of the function that I plotted in here, the derivative of the power. This is my power function, the one that we were talking about in here. Okay, of course, the derivative can be positive or negative because this function was growing, and then at some point it's decreasing, so the derivative better be negative to reflect that decrease. Okay, so let me go back into my notes in here to try to finish the idea of the power. Now, we didn't calculate the power across the resistor. The power across the resistor is going to turn out to be the exact same expression, okay? Because it's going to be the voltage across the resistor times the current across the resistor. Let me go back into my expressions in here to tell you how this is. I think it's part of the lab activities too. But just to refresh our minds on the lab, I know some of you did not make the lab. So the power across the resistor is going to be this voltage across the resistor times this current that is flowing through the resistor. You have a V naught squared over Z. You have an R over Z times V naught. But you have cos times cos, only the average cos squared is going to be 1/2. So you're going to pull it 1/2 again. They're in good shape. And it's exactly the same number as the power from the power source. Which makes you wonder then, what happened to the power across the capacitor and the resistor on average? Well, either they cancel one another, which doesn't make sense, the power is always positive, or they're going to be 0 all the time when you average them. And the latter is the real case. Namely, they will have an average of 0. Because you will have VC, which has something times sine of omega t minus phi, and I sub t, you have something times cosine of omega t. Now you have a sine times cosine, that's a sine of twice the argument of the angle. It doesn't matter at this point what's going on because you're going to average it over a long time. It's going to be 0. Sine times cosine is going to be sine twice the angle. So it's actually, its periodicity actually doubles. I mean, its frequency. So instead of seeing 60 times in a second, you're going to see 120 times every second. So if you had a justification doing the average for a single signal at 60 hertz, you will have twice the reason to do it for this one. Twice justification to do it for that one. So on average, you will have 0 power consumption in a capacitor because at some point you're building charge in it. So it's opposing that, doesn't like to build charge on it. But once the charge is built in it, it's going to be a power source. It's going to deliver that charge back into the system. So the capacitor doesn't really mind, doesn't dissipate energy at all. Takes it during the buildup of the energy, consumes energy. During the release of the charge, because it's going to discharge, it's going to give it back. So the capacitor, on average, has no power consumption whatsoever. Same thing, the story is happening with the inductor. You have a sine and a cosine. When you're multiplying them, it's the same thing. When you average them, you're going to get a 0 because for the same reason. Sometimes you're trying to push the current and the inductor doesn't like current increases. Once it has a current established and you try to decrease it, now it's going to push energy into the system, trying to prevent it from decreasing. So the inductor also builds up energy during half of its cycle and releases it during the other half. That's why on average it has no power consumption. So the entire power, what is it consumed? It's consumed in the resistor. And that's exactly what's going on. If you average the power on the resistor, you'll find out exactly how much you delivered from the energy source, and that's a check on your side because you expect the energy to be conserved. That's something that confirms something that we knew from time and time before, that the energy must be conserved, whether instantaneously, of course we do it instantaneously, we're going to find it also conserved, or on average. And that's what we're saying in here. On average, the capacitor is building up energy at some point and then releasing it in the other time. So in an average, I will find 0. And the same thing is true for the inductor. If I'm building current, establishing current, at some point it's going to push it back, trying to prevent it from being de-established, if you wish. You see the story now of an RLC circuit? That is actually everything in terms of resonance, in terms of everything. Now, I didn't talk about the phase, and the phase is another thing also that's going on in terms of the phase. Because this thing in here, the phase has tremendous implications also. The phase is equal to the arctangent of omega L minus 1 over omega C over R. So the denominator in here just is a scaling factor, basically trying to make when this transition happens between these two. So it's going to make the curve either very sharp or broad, okay? Now, for high frequencies, 1 over omega C is 0. So you'll have looking at the arctangent of infinity, basically. An arctangent of infinity, positive infinity, is pi over 2. So this is pi over 2. Okay? And for very low frequencies, when omega is very tiny, this is 0, when omega is very small, you will be left with minus 1 over omega C, which is very big and negative. There's going to be an arctangent of negative infinity, and that is negative pi over 2. So it's here, negative pi over 2. Anywhere in between, the transition in here happens exactly at omega naught. This is not ifs or buts about it. At omega naught, these two will be in sync. And by the way, I'm sorry, I said something. For the power, it peaks exactly at omega naught. Okay? So that's correct, okay, if we took the derivative. So this thing in here is basically for the phase. Now, remember, R makes the signal sharp, the reception sharp, because you can fine-tune, change C, for example, and the curve moves one way or the other. So if you have a station that is broadcasting a certain omega, you can change your omega naught so that your receptor has a peak value at that frequency. Now it's receiving the maximum power, and it's basically in resonance with it. So you can use it now and amplify it and do whatever you want to do with it. Now, that's making R very small, okay? By making R very small, the signal is peaked, and it's very high peak, but also is very narrow. Same thing in here. That broadness basically depends on how it is, okay? The transition could be like this, or could be like this, depending on how R is. But at the end, you start from negative infinity and positive infinity. I did not plot that one, but I think you guys can see the picture. But this is how this thing will work. The entire chapter talks about the AC current, actually, but it's taking the RLC circuit as the example, and we took the RLC circuit. I know homework problems 54 and 55, they give you guidelines basically on how to tackle them using, if you wish, as long as you follow the steps, you shouldn't be wrong with them. So the entire chapter is on the RLC circuit. Granted, AC circuit is much, much broader than this one. If you guys are going to be taking circuits later on, you will see far more to the topic than we just covered. You will see a lot of the circuits that have different things back and forth. And there is one point in here in this chapter that we need to talk about, and I did not mention it earlier when we were doing chapter 30, but I think it's important. And that is the voltage across we still have about 3 minutes. I think we can finish it. Remember, we have this device that we talked about, namely the transformer. Okay, the transformer has a primary EMF and a secondary, basically. The current in the primary is proportional to basically, at the end of the day, if you guys remember, there was a minus sign, forget minus sign. The EMF in the secondary has to do with the number of turns that it has in the secondary times the linkage, basically drop in the linkage of the flux, linkage flux in the place where they are linked, basically. So that's the expression we saw last time, and you could argue the same fashion in here, that the EMF also in the primary is in a similar fashion, is equal to how many turns I have in there times the linkage also flux, the rate at which it's changing. This is time dependent. Transformer cannot work in a DC circuit. Now, if I do the ratio of these two here, I will find that the voltage across these two, primary and secondary, is proportional to the number of turns in the primary and secondary. So I can have I think I remember now, probably we discussed this point when we did this. I could have a voltage basically increase or a voltage drop using this ratio in here. I think we did. Step up or step down transformer depending on this ratio. So if I start with 120 volts, which is most of applications, and I want to use it on my laptop, which requires, for example, an 18 volts, then 18.32 volts, for example, or something like that. So this is a step down transformer. So if I look into my power supply in there, there is a transformer in there that ensures that the ratio of the number of turns in the secondary to the primary is the same ratio of 18.2 divided by 120. So that's basically how the transformers work. If I want it to be a step-up transformer, which is usually in the power company when they're sending signal, then they do the reverse, basically. Take a transformer, and if somehow you can push the power from the secondary, it's going to act as a step-up if it were a step-down transformer. So this is the entire chapter. I think the content is there. I think you should be able to do your homework problems. And unless you guys have any questions related to this topic, because I think the time is up right now, we should be good. Let me take the people who attended the second session. I know that some of you have to go to work earlier today, and I wanted this to be taped and recorded as soon as possible. Okay. I'll see you guys Thursday.